Can I start? So welcome everyone. It's a pleasure to have Dana Zilberberg from Rutgers. So she will tell us about inverse problem and transmission eigenvalues. Please.
Thank you very much. I'm very happy to be here, and it's been a great time. So thank you to the organizers, and it's a great pleasure to be here. So I'm going to be talking about what I've been doing in the past couple of years for my PhD with Firal Bakakoni and Michael Fogelius, my advisors. And we come from this work is related to scattering theory and the inverse problem with a fractional equation. So fractional Helmholtz equation, what I mean by that is the following equation. So instead of the classical Laplace plus k-square operator that you have for the Helmholtz, you take a fractional Laplacian. Fractional Laplacian means the inverse Fourier transform of that norm of xi to the 2s of the Fourier transform. So it's inherently non-local, and it's very different from the usual intuition you get when you do local problems, Laplacian, and you don't have integration by parts, so they're very different. So a lot of tools are very different. And this equation models, I'm not very familiar with the physics, but from what I understand, it models wave propagation in complex or attenuating media, where non-local properties happen. And if you take the case s equal to 1/2, so in this talk we are going to consider the power to be between 0 and 1. And if you look at s equal 1/2, it actually describes a system of a photon interacting with a system of two-level atoms. And you can read that paper if you want to know more about it. Okay, so what do we know about this equation? Well, the solution, one type of solution would be this plane waves. So just for Helmholtz, the plane wave, which is e to the ik theta dot x, is a solution of this fractional equation in the whole space. And in general, solutions to this homogeneous equation, we'll call them incident fields. And what we want to do with that is a scattering problem. What is a scattering problem? So suppose your background media is 1, except in a compactly supported region, which we will call D, where it's a function. The index of refraction is a function, n. And so you want to compute a field solution of that fractional Helmholtz equation in the whole of RD. So we are working in the whole Euclidean space. We're not a compact domain or anything. We're in the whole space. And you send an incident field, and the total field will be the sum of that incident field, and however it interacts with that media is the scattered field. And the total field is the sum of those two things. So this is the same setting as for Helmholtz equation, but when you have the Helmholtz equation, for this problem to make sense and to be well posed, you need to impose a radiation condition, which is called the Sommerfeld radiation condition, and is the following. So it tells you something about the function at infinity. So partial r minus IKU will be the outgoing one, as opposed to the incoming one, where you would have a plus sign.
So n is a compactly supported function.
So n is 1 everywhere, but n minus 1 is a compactly supported function.
Okay, so good. So it's just basically a characteristic function. Yeah.
Yeah. So n is a function here. We will consider L infinity function, bounded function. And outside of D, it's just 1.
And inside of D, 0.
And inside of D, it's a function, L infinity function.
L infinity.
Positive L infinity function.
This is what.
Yeah. Okay. Okay, so is the setting clear?
Yeah.
We're probing something, some domain, scattering. Yes. Right. So, okay. So we need, in order to make sense of that problem, we need it to be well posed. So we need to find such a condition at infinity. For the field that is scattered, we need to impose something at infinity. Otherwise, there would be too many solutions. So what should we consider with this fractional problem. Because you see, it's not obvious that this radiation condition would make sense, because we're taking a derivative there, and this problem a priori is of order s, and s can be small, so maybe there is not even a derivative. I mean, how do you make sense of this? Is it the right thing to consider? And one thing that could help us is also, okay, what does the fundamental solution look like? Because if you know the fundamental solution, then you can tell, okay, fundamental solution satisfies a certain radiation condition, maybe that's the right one, and then we can prove some uniqueness. So these two questions are related, and it would be anyway interesting to have a fundamental solution to be able to compute solutions. Once we have this well-posedness, what type of inverse problem can we solve? By inverse problem, we mean, okay, given some data on your U solution, can you recover information on your N? What was N in the beginning? Okay, so to answer those questions, in the first part, we'll consider sorry.
Include also identifying D, or D is given?
No, D is not, N, yeah, D is related to wherever N is not 1, that's D. So if you know N, you know D. So D is an unknown also. So in the first part, we'll talk about the well-posedness, and I'll show you how to compute a fundamental solution, how to prove a certain radiation condition, which turns out to be the Sommerfeld radiation condition. We'll show you the uniqueness, the well-posedness of the direct problem. And once we have that, we'll go to the inverse problem, where in fact we will recover that D, but not the full N. I was only able to show we can recover the support of this N-1, but not the full function. Okay. So how to compute the fundamental solution? Fundamental solution will satisfy your equation with a Dirac delta function on the right-hand side. So when you take the Fourier transform, it's in the end you want to compute that integral there, which has a pole at k, so on the real axis. And one way of computing this is by limiting absorption principle. So instead of considering k real, you give it a small imaginary part. So you pull the pole in the upper complex half plane. You could do the same in the lower complex half plane. And then you do a contour integral in the complex plane. So if you're in RD, you do spherical coordinates to bring it back to an integral over 0 to infinity. And okay, when you do that contour, you see you want to compute this integral over here. So you say, okay, it's the sum of those two terms plus the residue at the pole. And essentially you want to say, well, that part goes to 0 as the parameter r goes to infinity. And that's not that trivial. You see, for example, if you look at this integral in 3D, you will have a r squared coming from the radial coordinates over r to the 2s. When you integrate the exponential, you get to 1 over r. So in the end, you get something like r over r to the 2s. And when s is small, that doesn't go to 0. So there is some work to do there. When s is large, maybe it's okay, but otherwise, we need to find a way to compute that integral. So we use some algebraic trick. I'm going to pass the details because they're very heavy computations, but essentially the idea is you have this algebraic formula there, so you artificially bring a higher power on the denominator by, some algebraic trick, okay? And you're able to have that part of the contour going to 0. But bottom line, what's interesting, so you get two terms, right? The term from the residue and the term from the imaginary axis where you integrate. The term from the residue is going to give you a multiple of the fundamental solution for the Helmholtz equation, the local equation, the local operator, the well-known fundamental solution for Helmholtz. And then you get a second term, and this second term is well-behaved in the sense that it's going to decay faster at infinity than the Helmholtz. So it has a stronger singularity around 0, but at infinity it decays faster, which is interesting for us because we're looking for a radiation condition, so we're interested in the behavior at infinity. Okay, you can show that this, this fundamental solution gives you the space you expected. So when you take a convolution, it's in H2S, weighted. So you have a weight delta. What I mean by this is this definition there. So you take the Japanese bracket weight. Okay. So as I was saying, this term decays faster at infinity than the Helmholtz part. So when you try to apply the Sommerfeld radiation condition to that fundamental solution, it's going to work. This satisfies the Sommerfeld radiation condition because the first term does, the Helmholtz term, and then the second one just decays faster. So the sum of, you have a derivative term and a IK multiple, and it just decays fast enough. Okay, but that's not quite enough. Now we have a fundamental solution which gives us existence of some solutions that are radiating in the sense of Sommerfeld radiation condition, but doesn't show us that these are unique. So we still need the uniqueness result, saying, give me a solution that satisfies the homogeneous fractional Helmholtz and that is radiating, then it should be 0. We need that result. So that result is actually easy and not so easy. Easy because solving the homogeneous fractional Helmholtz implies that you're a solution to the homogeneous Helmholtz. Quick way to convince you, if you take S equal to 1/2, okay, just the identity that we all know. Okay, so if you're a solution to the fractional, then if you're in the kernel of this, you're in the kernel of that. Now, not so easy. Okay, for S equal 1/2, it factors very well. For S between 0 and 1, you have some weird things, okay? And you need to make sure, okay, in what sense are you talking about this? If you look at this, if you want to be solving homogeneous Helmholtz in the sense of distribution, and you use that factoring argument, essentially you want to apply all these factors on the test function, which is a Schwarz function. But it's not that easy, right? Because that operator doesn't preserve Schwarz functions. So remember that the fractional Laplace operator has a non-smooth symbol, right? So when you take a Schwarz function, this is still a Schwarz function, but you multiply by something that's singular. So in the end, you get something that's smooth, but not decaying as faster than any polynomials, right? So you're not a Schwarz function, but you're still decaying somewhat and enough to be in this space L2 delta. So that's sort of how you need to be careful with things, but the basic idea is very simple. Okay, so this gives us the result, right? Because if you're radiating, solving the fractional Helmholtz, then you're solving Helmholtz. And we know that if you're solving Helmholtz and you're radiating, you're 0. Essentially, Sommerfeld radiation condition provides uniqueness of solutions for Helmholtz equation. Okay, so this brings us to that nice well-posedness theorem that tells you take a solution in this space, weighted space, H2S minus delta, with a compactly supported right-hand side F, and you satisfy the Sommerfeld radiation condition in the classical sense, is equivalent to being the convolution with that fundamental solution I told you, I gave you. So this can actually, we did even more than this. You can extend the right-hand side to be non-compactly supported. You can extend it to some weighted space, and this is done via resolvent, limiting resolvent operators by the work of Ben Arce, Nemirovsky. I didn't cite them here, but also one interesting thing is that all of this was done for S equal 1/2 by Umeda, And this is what inspired a lot of our work. Their proofs inspired a lot of our work, but you saw the case S equal 1/2 is somehow it's a very particular case. It simplifies a lot of things. Okay, one sort of open questions we might ask is, okay, is this zone of radiation condition still the right one to consider? Isn't there a better condition in the sense have a lower derivative in it? I don't know, but I think that the Sommerfeld is the right one. But maybe there is a better one in the sense that it's involving a less order derivative. Okay, so now that we have this well-posedness theorem, we can talk about the scattering theory, the inverse problems, and all this. So recall that what we're interested in this inhomogeneous media n, okay? n-1 is compactly supported in D. And U here is the scattered field, so you want it to be outgoing in the zone of radiation condition sense. And we just showed, okay, this now should be well posed because it's given by the convolution with the fundamental solution we computed. And when you write these integral equations down, you arrive at a Lippmann-Schwinger equation for the total field. So identity minus this convolution operator, which is smoothing, right, because it goes in H2S. So it's actually a compact operator. It's a compact operator, and it depends nicely on K. So you can invert it by analytic Fredholm theory. When you take K small enough, you make the norm of that compact operator small. So you say, okay, it's invertible for some K. And because it's continuous in K, it should have only discrete number of Ks where it's not invertible. And those Ks can accumulate only at infinity. For real ones, I'm talking about. Okay, so this discrete set, lambda, we call them scattering poles. Okay, this is where a priori you cannot invert this. So for the Helmholtz equation, there are no real scattering poles. They're complex. And I would like to show that these ones too are complex, but I haven't been able to. So, okay, scattering poles, what does it mean? It means you can find a solution to your equation, homogeneous equation, that's radiating. And we can show that if you take a positive imaginary part bounded below in some open subset, then there are no scattering poles. Or if you take your n to be small enough, there are no scattering poles. But in general, this is open. We don't know if there are real scattering poles, but I think they're not there. We can also relate them to something else. What I've been talking about before is this limiting resolvent operator. So you take your operator and you take the limiting absorption principle. So these, by the theorem of Benartzi and Nemirovsky, the limit of this operator exists, but you have to exclude a set of resonances of poles. And this set depends on K, because you see it's not quite Schrödinger, it's like multiplied by the frequency there. So your set will depend on K, and you have to say essentially that K to the 2s is not in this set depending on K. So I have no clue how to prove this. But the two things are related by saying, well, if you have this eigenfunction there, then it's an eigenfunction for that operator, so your K to the 2s is in this lambda K. But the converse is not true, because if you have an eigenfunction for this, it might not be radiating. That's how the two are related.
When you say n is real and small enough with respect to what?
Small enough depending on the Dirichlet eigenvalue for D. So it comes from estimating your integrating your equation, integrating by parts, and you have this Dirichlet eigenvalue that comes up. And you take small enough, you can make things positive. Okay, so we have to, okay, bottom line, we have to exclude a set, discrete set, of scattering poles if you want to talk about a scattering problem. We have to exclude them. Okay, now I told you we're going to solve an inverse problem, but what is the data? What do you know of your experiment? So you're going to send plane waves on your D. Plane waves of the form, remember the e to the ik theta are solutions, so they are incident field. You probe your media with those directions, in every direction is theta, and you let it scatter, and you measure your scattered field far away. Far away because remember that the fundamental solution gives you Helmholtz plus something that decays faster, so far away, it looks like Helmholtz far away. And Helmholtz far away behaves like a spherical wave. So when you look at the asymptotic of your scattered field, you actually have this spherical part, the complex exponential there, times some angular function. And this angular function, so corresponding to the incident plane wave theta, you measure it in the direction x hat, and that gives you a matrix, right? I mean, this u infinity, okay, we call this a far field pattern. And that's your data. Basically, you measure the scatter field far away for every possible incident direction, every possible measurement direction. From that, you can even superpose your incident plane waves on the circle and create an operator from that far field pattern, which we call far field operator. So you see, you superpose your incident functions with some potential g on the sphere, and you measure the same. So it will be the superposition of your far field patterns on the sphere. So that's our data. Okay, so as I said, you probe, okay, with theta, angle theta, scatters, you measure in every x hat possible. We will need a few assumptions on the n and the d for this inverse problem to work. Namely, we will assume that n is real valued, that n minus 1 is bounded below, so it doesn't go all the way to 0. And your d is compact simply connected. Okay, then we will use an argument that is very beautiful, and it's done by Kirsch and Winberg for the Helmholtz setting. So essentially, what it tells you, in the Helmholtz setting, you have the same operator, the far field operator, and you can factor it in the form BA B star, where A and B satisfies a bunch of properties, and importantly, your F is injective. Then this theorem tells you, it's a purely functional analysis theorem that tells you, well, if we can factor this operator like this with these hypotheses, then the ranges of f star f to the 1/4 and the ranges of b are equal. So if the operator b has a range that somehow characterizes the support of your inhomogeneity, then your far field operator, in this weird sense, characterizes also the support of the inhomogeneity. And that's what happens. So for Helmholtz equation, you do this factorization. I pass the details. But I bring your attention on one of the conditions is that the far field operator is 1-to-1, so injective. It's not clear whether it's injective. You have to exclude, again, a set of frequencies, which we call transmission eigenvalue. And Fioralba made a beautiful talk on the transmission eigenvalues for Helmholtz. So they exist. They're an infinite sequence that goes to infinity under certain assumptions. And here we have again the same. Another transmission eigenvalue problem, different from the Helmholtz one. You see, it's going to be like this. So if you remember Fioralba's talk, you have the same problem, but you add this term coming from the other term from the fundamental solution, this phi delta. Okay. Except for that term, it's the same problem. Okay. So where does it come from? It comes from just directly trying to show your far field operator is injective. You take a g in the kernel of your f. You say, okay, suppose this is 0. Then can we prove that g is 0? Okay, so then the Helmholtz part will have a 0 far field pattern. That's what it tells you. And there is a lemma, which is called Relish lemma, that tells you if your far field pattern is 0, then you're 0 all the way up to the boundary for Helmholtz solution. So that will be true for the Helmholtz part of your function. And that Helmholtz term will satisfy a certain Helmholtz equation in D. So you bring back the problem in a bounded region to a problem in a bounded region. And okay, but then we need to know there are no non-trivial solutions to this problem. And that's exactly what being a transmission eigenvalue and not being a transmission eigenvalue would mean. So we need to exclude the possible frequencies k for which there exists a non-trivial solution to this equation. Okay, is this a big set? As I said, in the Helmholtz case, it's just a discrete sequence that goes to infinity. It's not dense, it's not big. Do we still have this? We can indeed, with the same very similar arguments, prove that it's not big, it's discrete, easy to see. You bring that to a fourth order problem, you move around the terms, you get this fourth order problem, and if you bring the higher order term, you have 1 over n minus 1, so you see this is where the bounded below, you have your n minus 1 to be bounded away from 0. This comes into play here. And you take the highest order term, which is Laplace v Laplace phi, you bring that in an operator A0, which is going to be coercive, because if you control Laplace on H20, you control the whole thing. And plus some operator, which will be all the lower order terms, so it will be a compact operator, depending on k. Depending on k smoothly again. And again, you can use the Fractional analytic theory to say, well, invertible plus compact operator, depending smoothly on k, you can only have a discrete sequence going to plus infinity. So this is nice, but you can even do more than this. You can do more with this beautiful argument of Furalba, Keokoni, Jurosov-Gintides, and Utsanada. So they prove the existence. So not only this sequence might be there and is discrete, but it exists, it's actually there. So, so we have the same for this fractional problem. You see, it's not changing too much. It's just we have to take care of that convolution term there for things to work out. So again, you write that fourth order problem, you extract what looks like Helmholtz. So this will be exactly the Helmholtz problem perturbed by some convolution term there. But what's nice with that convolution term is it's signed. So it has a sign. And the argument is the following. So it's quite nice. So you put an artificial lambda k in front of the ak. Then lambda k is an eigenvalue of this b, which is compact. So you have the Courant-Fisher min-max formula, which tells you the jth positive eigenvalue in decreasing order is given by this max over subspaces of dimension j of the minimum of the subspace. Okay, so in particular, your artificial lambda that depends on k is a function of k, and it's a continuous function of k because it's given by this ratio there. So if you can somehow prove that at some point it's below 1 and at some point it's above 1 by just intermediate value theorem, you know that it's 1 somewhere. There exists a k for which this lambda jk is 1, which tells you that ak minus bk is 0 for some eigenfunction. So how do you do this? So when you take k small enough, the term bk can be absorbed into the ak, and you'll have the positivity of your your bilinear form everywhere. So you can, this immediately tells you that the lambda j of k are below 1 for k small enough. Now we need to find another k for which this lambda j of k is above 1. So what they do is they take balls of radius epsilon, they fit it in the domain, and they say we know the eigenfunctions for the ball. And the eigenfunctions for the ball, if you take the balls to be disjoint, they're going to create a subspace of dimension whatever you want, however number of balls of radius epsilon you can fit. And this gives you a subspace where this form is negative. And then you know that you have that for any j you want. So you have, every time you have a k for which the lambda j of k is 1. That's how you obtain the existence. Okay. Back to the factorization of your far-field operator. So now we know that the far-field operator is injective, provided you exclude the scattering poles and provided you exclude the set of transmission eigenvalues I just showed you that exist and is a sequence going to infinity. So if you exclude those k's, you have this nice factorization where you see you factor it with a g that gives you essentially the far-field pattern for a Helmholtz equation there. And this is where everything comes to play, because we know that the range of this G characterizes the support of your inhomogeneity. By saying the range of G contains the far-field pattern of a point source if that point is located in D or not. That's how you obtain the results. Okay, so remember the Kirch-Greenberg factorization theorem tells you the range of f star f to the 1/4 is equal to the range of G, because we were able to satisfy all this list of hypotheses on the various operators. And so in a more simple language, what that tells you is that if you do your experiment of sending your plane waves on your domain, you measure what is scattered. You do that for every possible angles. Suppose you have two domains that give you the same far-field operators, then you know that these two domains have the same shape. They're the same. But it doesn't tell you that the function inside the n is the same function. That's what's missing. Okay. So okay, so now I'm gonna give you some numerical experiments that I did to make sure that all of this nonsense works. So remember that your total field is given by the Lippmann-Schwinger equation. So provided k is not a scattering pole, but numerically, I mean, we don't know, we just invert. So you do this identity minus, so here's going to be a matrix, right? You, how do you say, you discretize everything. And you invert that big matrix to get your total field. So this is only inverting, you only need to invert over whatever is the support of your inhomogeneity. So here is this boomerang-like shape. And when you want to extend it to know it outside, you just use the convolution formula with the fundamental solution that we have. So if you do this, you're able to compute the whole thing. And it looks like waves, right? It looks like, you see that the incident field was a plane wave going in this direction. And when it hits the inhomogeneity, it scatters, it modifies the field. And this is the scattered field. So it's like your total field minus the plane wave that you sent. Okay, so then how do we solve the inverse problem? So remember, the inverse problem is saying, look at the range of your far-field operator. So your far-field operator is now something that, in terms of each incident angle, measures at each measured angle the far field, how your field looks like far away. So you can compute that numerically. It gives you a matrix because you discretize everything. So here it's for 36 incident angles, 36 measured angles, so every 10 degrees. And then you look for this phi infinity. This phi infinity of z is the far field pattern for a point source at z. Point source means, in 3D, e to the ik modulus of x over x. That's the point source at 0, so you do x minus z. And this gives you a spherical wave from that point. So you look for that in the range of this f star f to the 1/4. And when you invert, if the z is in D, you'll find, and if it's outside of D, the norm of G should blow up. So what you plot is exactly the inverse of the norm of G somehow. And that should be small wherever you're not in D. And okay, so these are some results. So you take, I took, this rectangle and a circle, and I played with the S. So this S equals 0.2, 0.7, and this is Helmholtz, so S equals 1. It seems to work, although there are some noise and some things. I don't know why the Helmholtz case doesn't work as well. I have no clue. Maybe my code is not great. I don't know. And then I changed the frequency. So here k equal 2, k equal 5, and here k equal 5 with more incident angles. Again, I would expect that when you increase the frequency, you should recover something more precise. But again, I don't know why this is doing this. But when you increase the frequency, you also increase the oscillations, and you need to have a proper discretization. So maybe there's something about this as well.
So your theorem includes domains that are not connected, or here it's just the numeric for when you have this? So these two objects, like a rectangle, and these are like the...
Yes, that's the...
And you said that you have the assumption that these connected, but here you don't care.
Yeah, no, I meant it doesn't have Holtz. Yeah, sorry.
Oh, okay.
Yeah. But yeah, when it's, doesn't have Holtz. Okay. So conclusion is that we proved the well-posenness. We said that the Sommerfeld radiation condition ensures the uniqueness of solutions to the fractional Helmholtz equation. And we were able to compute by limiting absorption principle that the fundamental solution was the sum of two things, a multiple of Helmholtz and something that decays faster. From that, we're able to define a far field pattern because it takes the behavior of that first term, because the second one decays. And we're able to make the scattering problem work provided we exclude some scattering poles where we cannot invert it. So provided we exclude those scattering poles and provided we exclude those transmission eigenvalues, then we are able to recover from that far field data the support of the inhomogeneity. Now there's still a few open problems there, so of course recovering the whole function would be nicer. Proving that the scattering poles, there are no real scattering poles, would be also nice. And yeah, so that's it. Sorry, I'm very early. Thank you.
Question, comment, Donna? Maybe I start with, so when S goes to 1, do you expect any similarity to the actual local? You said that when n is small, you can say that there is not real a scattering pole. If S goes to 1, you could say something similar,
I don't think so, because it's really, the case S equal to 1 really marks a threshold. It's really, anything below 1 will be completely non-local, so it's very different. I guess you can make things tend to the case s equal 1 in some sense, but I don't expect, you need to find other arguments. The arguments for the local case do not apply for the fractional case. So
Just continue and ask my question. What's happening, say, to transmission eigenvalues when s goes to 1? Is some continuity or?
I don't know. I don't know. All we have is the existence of the transmission eigenvalues. So this is a sort of a non-constructive argument. You don't know what they look like. But I'm actually looking at, I'm trying to figure out what they look like for a ball. And I haven't been able to do it so far because it involves, it's not as easy as the Helmholtz case where you have the zeros of Bessel functions and it's very nice. But the fractional case, again, it's heavy computations and it doesn't split in a nice way. So, but I'm looking. Maybe it will have some similarities. Maybe it will go to the transmission eigenvalue of the Helmholtz case when you make s go to 1. Maybe.
But maybe those operators do not look to behave continuously as it's singular.
Yeah.
Actually, many people are trying to use fractional uniqueness, say for conductivity, even for, and then they would like to take the limit to go to, because you get stronger results for fractional. You let the limit go to 1s, but it's a completely singular. It's just you don't recover the local case.
No.
But here Dana said we haven't tried.
Mm.
For the inverse problem, how do you synthesize the data? So how do you solve the forward problem?
Oh, right. So for that, you have the convolution with the fundamental solution, right? So so that you can implement that convolution, and that gives you the solutions for the forward problem. You
You have to discretize it.
yes. Right. You discretize. You take your right hand side, compactly supported right hand side. You take the integral. The integral you discretize into a sum. You take each point. You take just the function evaluated at that point, the fundamental solution evaluated at xj minus yj, and for the singularity, I do the ball. I integrate over a ball. The singularity, so it's an approximation, but that's how I do it.
Any other question, comments? If not, let's thank Dana again.